Adiabatic, and isentropic steady flow. As mentioned in previous section, the isentropic approximation greatly simplifies a compressible flow calculation. So does the assumption of adiabatic flow even if non-isentropic. Consider high-speed flow of gas past an isolated wall as shown in this picture. There is no shaft fork delivered to any part of the fluid, therefore very stream tube in the flow satisfies the steady flow energy equation in this form, as we have the energy equation. Where point 1 is upstream of point 2, you may wish to review the details of this equation in previous chapters, especially chapter 3. We saw in this previous chapter, in chapter 3 example, that potential energy change of a gas are extremely small compared with the kinetic energy and enthalpy term. We shall neglect the term Gz1 and Gz2. Inside the thermal and velocity boundary layer, in this picture, the heat transfer and viscous work term Q and WV are not zero, but outside the boundary layer, Q and W of viscosity, work of viscosity, are zero by definition, so that the outer flow satisfies the simple relation as H1 equals to constant. The constant is equal to maximum enthalpy that fluid would be achieved if brought to rest adiabatically. We call this value H0, stagnation enthalpy constant. H0 of the flow. Thus we can rewrite the equation as this expression. This should hold for a steady adiabatic flow of any compressible flow outside the boundary layer. The wall in this picture, as shown, could be either the surface of an immersed body or the wall of a dart. We have shown the details of this picture. Typically, the thermal layer thickness is greater than the velocity layer thickness because most gases have a dimension Prandtl number less than unity. So we can write the thickness thermal thickness, delta T is greater than the velocity layer thickness delta V, because the most gases have a dimensionless Prandtl number PR less than unity for the gases. Note that the stagnation enthalpy varies inside the thermal boundary layer, but its average value is the same as that of the outer layer. Beauty is related one. For non-perfect gases, we may have used to use EES or steam tables or the gas tables to implement, but for a perfect gas, so let me write for the non-perfect gas. We can use EES tables, and for the perfect gas we have a relation for H in this equation. So we can write the equation again. Here we have this relation, stagnation enthalpy for the perfect gas, CPT This establishes the stagnation temperature T0 of the adiabatic perfect gas. Stagnation temperature the temperature is achieved when the accelerator to raise adiabatically. This equation and alternative to this equation also occurs when the enthalpy and temperature drops to zero, so that velocity achieves a maximum value when the enthalpy and temperature drop to zero. Drop to zero. Vmax, the maximum velocity equals to 2 No higher flow velocity can occur unless additional energy is added to the flow through shaft work or heat transfer. Mach number relation